Hello everybody and welcome back to the Amarculus channel. Today we're going to be solving a quite complicated problem. This was a problem that one of my friends was struggling on and I decided to make a video on it because it's pretty unique. So yeah, let's get right into it. And it has some pretty cool concepts of calculus, the fundamentals, but they're applied in a cool way. So yeah, let's get into it. So the integral here is the integral of x times e to the nx all over nx plus 1 squared. So this quantity is squared like here. And it's differentiating with respect to x. So n here is just an arbitrary constant that can be used here and right here, of course. And yeah, we see e everywhere, so that's just Euler's number. So yeah, let's start integrating. So number one thing to look at here is, do we have a u du situation here? So is there anything we can say we can let equal u, and then everything else can be a du? So in this case, let's say we let u equal nx plus 1 in this case. Du is equal to n just by differentiating. But do we see an n up here that we can just substitute for u at the bottom? No. Now, this thought process is, it's a thought process, but in this case, it doesn't work out. Because if we do something like this to substitute an n here, so we can use u substitution, what happens to the x times e to the nx? We can't really resolve this term. So u substitution is not the right approach here. Today, we're going to be using a technique called integration by parts. Essentially, it's just the closest thing we have to product rule, but for integration. So consider this. If we have uv and we take ddx of u and v are their independent functions. They're just functions of x. If we differentiate this, our standard product rule tells us this is u prime v plus uv prime, just like that. So all product rule says is, okay, we have this equality right here by this equation. Just integrate both sides. What happens? So the integral and the ddx cancel. So we have uv is equal to the integral of u prime v plus integral of uv prime. So just rearranging some terms, we have integral of u dv, I'm going to write it like dv, is equal to uv minus integral of v du, just like that. So whenever I see a prime, I just wrote du to indicate the variable of integration in this case. So yeah, that's essentially the integration by parts. You have something times something differentiated is equal to this and this. This is exactly what the formula states. And you'll see it in action today. So let's apply the formula. We're going to be using this. And this is a very fundamental part of calculus, if you learn in Calculus BC and other classes as well. So, moving on here, what can we set as our u and dv in this case? So, when we have an integral like e to the x sine x right here, it's pretty clear, dx, what we should set our u to be. U is equal to sine x in this case. And we have e to the x dx, this is all equal to our dv. Because you see here, we have to integrate dv to find v, to plug into the formula twice here. And e to the x integrates very nicely and easily, so we don't really have issues there. And it works well with the integral as well. So this is a problem I can do for another time, but our u and dv are pretty important. Now, let's say we try something unique for our u and dv. Let's say we do this is equal to the integral of, we just break up the numerator and denominator. Or we can even do something interesting. Let's do x over nx plus 1 squared times e to the nx dx, like this. So we can set this to be our u, and this can be our dv. Right? And I remember that I said the e to the nx is nice because we're going to be integrating the dv to get the v in the case. So let's say we try this. That means that our integral becomes integral of u dv e to the nx dx is equal to uv minus integral of v du. So we have to find du and v. In this case, du is equal to what? Now, the differentiating this is going to get a little messy. It's not hard, but it just gets unnecessarily messy. So maybe we have the wrong approach. Should this be how we split it up? Well, let's explore something different, because differentiating that is just going to make this more complicated via quotient rule and all of that. So what other options do we have? Another option is to switch these around. E to the nx can be the numerator, and x dx could be dv. Now, what's the issue with this? as I said, we want to choose a good dv because we're going to be integrating dv to get v, which we're going to be using in an integral later. And while we could just use x dx, e to the nx is a better choice because e to the nx just works better with integrals, and it doesn't get more messy because the integral of x is, of course, x squared over 2. So yeah, let's say we try the most obvious approach, or the less obvious approach, which is this. So we tried putting x on the top here. We tried e to the nx at the top here, but now we're trying just 1 and leaving this as x times e to the nx dx. So in this case, this means that this is our u and this is our dv. I'll notate this in different colors so you can see here. So what does that mean for us now? Let's find our du. Our du is a little easier to find right here. It's just differentiating this. So we have nx plus 1 to the negative 2. Differentiating this will give us negative 2 nx plus 1 to the negative 3 times n, of course. But wait, this power is getting it's getting less. It's becoming more negative, and that's not quite good, is it? Because when we're going to be integrating right here, this is our u right here, and when we're finding this integral, which is part of the formula, we're doing integral of v du. du is getting more massive, essentially. So maybe this isn't the right approach either. Let's see. So what other options does that leave us? We've tried nearly everything, but is there something we're missing? Yes. If we look closely, our grouping is correct. It's just the assignment of u and dv. So what if we said that this is going to be our u and this is going to be our dv? What happens then? When we have dv, that means we're going to have to integrate dv to find this v, which we're going to plug in over here. This is quite easy to integrate. 1 over nx plus 1 squared dx. That's quite easy. And our u, what are we going to do with our u according to the formula? We're going to differentiate it. Differentiating this is not that messy. Maybe we'll just have one extra factor, and we'll see what that is. So let's try this combination out. So that means that let's find du and v first. So du, right here, u is this. So using the product rule, we find that du is equal to e to the nx plus xn e to the nx, essentially, because we have to multiply according to chain rule. And now for v, what do? We have dv is equal to 1 over nx plus 1 all squared dx, and v is equal to the integral of 1 over nx plus 1 squared dx. We can use u substitution on this, of course. You can pause. I'll just do it for you guys. So u is equal to nx plus 1 du. This u is to not be confused with this u over here. So you can use a different letter. I'll just do that. A is equal to nx plus 1. dA is equal to n. We don't have an n up here, so we do n here, and we do 1 over n. That's valid algebra. So v is equal to 1 over n integral of u to the negative 2, I said a to the negative 2 dA. This gives us v is equal to 1 over n a to the negative 1 over negative 1 plus c. And we'll talk about the plus c in just a moment. But that means v is equal to negative 1 over a n. And what is a? A is right here. So n times nx plus 1, just like that, plus c. Now, when we're doing integration by parts, because we just solved for v, which is one of our variables for the integration by parts formula, we leave out the plus c normally because it gets quite complicated, and we just add it in at the end. It just makes it look more messy. So for now, I'll leave it in right here, but I'm not going to be using it when I insert v. So yeah, we have our u right here, du, our v, and our dv right here. So we're ready to do integration by parts. Now, let me move this down. What do we have here? We have the integral, I'll put it right here, integral of 1 over nx plus 1 squared times x e to the nx dx. And I'm going to switch this around so I can better label my integration by parts variables, like this. Okay, there we go. And I'll move this right here. So I said that this is going to be our dv, and I said this was going to be our, oh, I meant this is going to be our u, this is going to be our dv. Does that match what we say above? Yep, it looks like that's right. Okay, so moving forward, we said that this is, according to the formula, the integral of u dv is equal to uv minus integral of v du. So let's write it out. U is what? U is equal to x e to the nx. V is equal to what? Our v variable, we just found it. It is this. So it's going to be negative 1 over n times nx plus 1, like this, minus our integral of v. Where is v? Same thing, which is just this. Integral of v, negative 1 over n times nx plus 1 du. And what is our du? Our du is found right here. Now, we can simplify this a little bit just by pulling out an e to the nx. It would just be e to the nx times 1 plus nx, just like that. So I'm going to bring that down there. We're going to do e to the nx times 1 plus nx, or nx plus 1, all right? And what is our variable of integration? dx. So this is essentially our answer, but are we done yet? No, because we do have an integral in the answer itself. So let's simplify this more. I'm going to rewrite this, combining negative symbols and all that. So we have this is equal to, all right, and we'll call it orange. It's equal to xe to the nx times, I'll pull the negative out, 1 over n times nx plus 1, like that, minus our integral of, and I can pull this negative out, so that becomes a plus, plus our integral of, and I'll put this on top as the numerator, e to the nx times nx plus 1 all over n times nx plus 1 dx. Now, I'm sure you've noticed by now, but these nx plus 1s cancel on the numerator and denominator, which is really handy. So I can furthermore rewrite this. I'm gonna put this on top as well because it looks nicer. So we have this is equal to negative x e to the nx all over n times nx plus 1, plus 1 over n integral of e to the nx. Now, what is the integral of e to the nx dx? Of course, I'm sure you know it's 1 over n e to the nx, but you can, of course, use u substitution once again. So u is equal to nx. Du is equal to n, but we don't have an n here, so we can do n and 1 over n right here. So it's still multiplying by 1. And we just integrate, and then we get this. So yeah. Because we replace it with u, and then once we integrate, that's what we get. So let me undo this. That means, ladies and gentlemen, we have negative x e to the nx over n times nx plus 1 over n squared e to the nx plus c. Ladies and gentlemen, this is your answer right here. Negative x times e to the nx all over n times nx plus 1 over n squared times e to the nx plus c. Do not forget that plus c. I hope you enjoyed today's video. Catch you next time. If I made any issues or you have any questions, drop them in the comments below. So yeah, see you guys.